Hi, this is Paolo Ferro. I work at University of Padova, and with this presentation I'm gonna show you the results of an experimental investigation about the effects of different post-welding heat treatments on mechanical properties of the titanium alloy grade 5. Here the contents of my talk. I'll introduce the topic and the goal of the work. I'll describe the experimental procedure and the obtained results. And finally, as always, the conclusions. The joints under investigation, because of weight saving, are used in automotive application and must guarantee a static strength. Unfortunately, the toughness is found quite low. Therefore, post-welding heat treatments are required to improve the mechanical strength of the joints. Since in literature few works are found about this topic, new experiments aimed at optimizing the mechanical properties of titanium alloy grade 5 welded joints via post-welding heat treatments were carried out. The table on the top summarizes the chemical composition of the parent metal, while the table on the bottom collects the main process parameters, such as welding speed, voltage and current. It is noted that 2 welding runs were carried out for each joint using a filler metal with the same chemical composition of the parent metal. Both butt welded and overlap welded joints were tested. The plate thickness was 4.2 mm. Additional fixtures were bonded at the 2 ends of the single lap joints in order to assure a perfect alignment of the load during the tensile test. Samples were characterized by tensile tests, microhardness profiles and metallurgical investigations. The pictures on the top left shows the phase diagram in order to point out the values of the heat treatment's temperature, while in the top right you can see the recipes of the 2 different post-welding heat treatments investigated. Number 1, a stress relief heat treatment, and number 2, a partial solution heat treatment followed by water quenching and aging. The parameters chosen for each heat treatment are collected in the table on the bottom. Macrographs of as welded and heat-treated joints are shown in this slide. In all joints, the typical epitaxial grain growth was observed. Further, it is noted a prior beta grain size increase starting from parent metals and approaching the welding center line. In a first overview of the micrographs, nothing seems to change from the microstructure of as welded and stress-relieved heat-treated samples. These micrographs show the microstructure in different zones of the bead of both as welded and heat-treated joints. Heat treatments affect the shape of the elongated grain of the as received alloy by promoting an equiaxial morphology without increasing the grain size. Further, the increase of prior beta grain size from the heat effect zone to the fusion zone induced by welding was not affected by the heat treatment tested. Optical micrographs of the as welded joint fusion zones illustrate the dominance of acicular morphologies within the microstructure that seems to be mainly alpha prime martensite. Some thin layers of diffusional alpha grain boundary and retained beta phases are also observed. Alpha prime appears in the form of thin needles within the prior beta grains. The microstructure of the heat-affected zone of the as-welded joint is shown in this picture. It comprises both alpha and beta structures as well as acicular phases that seem to be alpha and alpha prime. During continued cooling, alpha plates nucleate at the beta grain boundaries and grow into the beta grain as parallel plates forming a so-called alpha colony. With increasing cooling rate, the size of alpha colonies as well as the thickness of the individual alpha plates becomes smaller. At higher cooling rates, alpha plates start to nucleate also at the alpha colony boundaries and start to grow perpendicular to the nucleation site, forming basket wave structure. The stress relief heat treatments didn't affect the original microstructure of the joints, while great amounts of coarse acicular alpha occurred in the fusion zone of SQA heat-treated joints. Furthermore, martensitic alpha prime is prone to decompose to equilibrium alpha and beta, even if the decomposition is not completed at aging temperature up to 600 degrees. These are the microhardness profiles as a function of butt-welded joints condition. All of them show a quite flat shape with a little increment of the microhardness by approaching the fusion zone. The lowest values are measured in the as-welded joints, while the biggest ones are observed in the SQA1 post-welding heat-treated samples. This is attributed to the higher amounts of alpha prime in the last ones, induced by the solution and quenching and only partially decomposed during the 1 hour aging heat treatment at 600 degrees. By increasing the aging dwell time, the increase in the composition of alpha prime reduces the hardness of the joint. Here are the core results coming from tensile tests. Stress relief heat treatment increased the yield strength of butt weld metal around 2%, but the toughness increment is much more significant. A longer dwell time doesn't affect the yield stress, but reduces the toughness because of the microstructure coarsening effect. SQA heat treatments applied to butt welded joint increase the yield stress from 10.4% to 12.5%, but the dwell time must be 9 hours long if at least the toughness of the as-welded joint needs to be reached. This is due to the increased amount of alpha prime phase in the microstructure of the weld bead after quenching, followed by its partial decomposition to equilibrium alpha and beta phases, according to the dwell time. Almost opposite result are obtained with regard to overlap joints. In this case, the strength increment promoted by SR1 and SR2 is about 26%, followed by an increment of the toughness values as well. The SQA1 heat treatment gave the worst results in terms of strength and ductility. On the other hand, SQA2 and SQA3 heat treatment increased the yield strength of butt weld metal around 10%, while maintaining almost constant the joint toughness. Finally, whole samples broke at the heat-affected zone. Okay, so with reference to our goal, that is the mechanical properties improvements of titanium grade 5 welded joints by means of post-welding heat treatments, we can conclude that the best results in terms of strength and toughness are reached with the stress relief heat treatments both for butt and overlap welded joints. SQA heat treatments are able to improve the strength only, not the toughness. Furthermore, be careful that quenching has the drawback to distort the joints. Well, this is me. These are my contacts. Thank you very much for your attention. Bye bye.